Recording answer.
So we can start with these 4 queens here, rotate the board, and put the corresponding queens here. There's a solution to the problem. There are 91 more solutions, or 11 more fundamental solutions. All right, so what's an approach that some of you were trying? You would write down a queen somewhere and then realize that caused a problem later. So you back up and erase some queens and back up to that point and try something different. Right? So an approach that is useful in terms of solving this problem sometimes is the idea of backtracking. Try something, get to a certain point, see what happens later. If that leads to a problem, back up, try something different from there. The first full backtracking solution to this problem came along, at least the first one that I know of was in 1972 by Dijkstra, who we will see quite a bit more later on in the next couple of weeks.
Dijkstra.
I've always heard of Dijkstra. Dijkstra. So that's kind of a brute force method, right? Try a queen somewhere, try everything from there, back up if it doesn't work. What might happen, you might end up trying queens in a lot of places that are never going to work. So it's beneficial to try to think of some situations where you don't want queens ever being placed, if that's possible, and to improve the efficiency of your program. Okay, now what does this problem have to do with anything? Well, when our good friend Max created this problem, it was strictly for fun, for intellectual, as a game. There have been lots of applications of the actual problem since. I mean, for one thing, it does just get used in the sense of showing people how to use backtracking, how to implement backtracking, so as an educational tool. But there are also applications to things like parallel memory allocation, a whole bunch of different problems that I've seen, VLSI design, a whole bunch of different things where the solutions to this actually have meaning. Okay, so this problem we're going to look into quite a bit. There are some other versions of this problem. In something like 2004, there was another chess site that created had a competition that said, okay, we have our 8x8 board, and we know that you can only put 8 queens on the board, so that no 2 attack. And they said, but if you take one of those solutions, and you look down here in the corner, if there's no queens in that corner, or there'll be at least one corner with no queens, I said, what happens? We could put pawns in these 3 squares and be able to fit an extra queen on the board. Right? So we could use 3 pawns to increase the number of queens to 9. Now that queen in the corner is definitely not attacking anything else, right? Nothing is attacking it. So if the other 8 aren't attacking each other, then that 9th one isn't attacking or being attacked either. Well, their question was, how many pawns do we really need on an 8x8 board in order to be able to have 9 queens? So 3 works, but what are we looking for? Maybe reducing that number. And so, after a little bit of experimentation.
Well, you could use 2 pawns in our past solution. In our previous solution, you could use 2.
So in this solution, where would you want to put pawns.
You could put another queen in like A8 and a pawn in A7 and B8. Right?
All right, so in this situation, we could add to that by putting a queen here, and then our pawns here, and there's no attack on that diagonal, and so that blocks the two. And so in that situation, we know that the number of pawns immediately can be reduced to only 2 pawns. Turns out that the actual solution is you can do this with 1 pawn.
I don't know about that.
Okay, now with 1 pawn, what does that mean? That means that if you take away the pawn and the extra queen that's been placed, we're going to have other things attacking each other somehow. Right? So the 1 pawn, it doesn't say that we start with an 8-queen solution and then add, right? We say, how many pawns do we need to be able to put 9 queens on the board? And so back in 2004, this started a few of us on some experimentation and some looking at this problem. The first paper on it came out in 2006, and then several other papers over the years looking at various versions of this problem of putting queens on the board along with some pawns to block. One of my co-authors from back then is working on a topic now, and I'm not sure how, well, he's posted it on social media, so it's okay for us to talk about it. Instead of the queens, or using pawns just to block between queens, he's looking at now how many pawns do you have to have in order to have everything be, say, 3 moves apart, all the queens being 3 moves, or being 4 moves, all the queens being 4 moves away from each other. So he's looking at, rather than just separating, this is called separation, rather than just separating queens, he's looking at distancing the queens. So he's, of course, now calling it socially distancing the queens. And so what happens to the original problem from 1848 if you, 156 years later, add a little twist to it to say, oh, let's increase the number by using pawns? Well, let's increase other things, right? Let's see how many queens you can put on if they all have to be a certain distance apart, as an increased distance apart. Okay, so what happens? The same kinds of ideas. How would we find out how many queens or how many pawns that are necessary? Again, we could do a backtracking solution. There's lots of other techniques that we could utilize. We're not going to really explore this problem much right now. We'll focus on the original, just the 8 queens, or on a larger size board, right? 9 queens or 10 queens or 50 queens on a 50 by 50 board. You can imagine that as the number of squares gets bigger and bigger and bigger, there's a lot more things that aren't solutions, right? What happens on a 9 by 9 board? There are how many squares? 81 squares. So 81 choose 9 possible ways to place queens. A lot of those, again, are bad solutions, or they're not solutions, they're bad attempts. So very few of them, relatively speaking, would be solutions to the problem. Okay, so we are going to utilize this idea as a starting point for our next main topic. And our next main topic is the idea of what we're going to call a graph. Well, not what we call a graph, it's different though than the graphs that you think of in terms of like the graph of a function. All right, so for our purposes, we're going to just be right now not very formal, just more intuitive with our ideas. So a graph consists of a vertex set and an edge set. A vertex set is just a set of objects. An edge set consists of pairs of those objects. So we're going to think right now of our vertex set as just being dots. So we have some collection of dots. Maybe we'll label them. And so each of these is a vertex. Plural of vertex is vertices or vertices. And an edge is just, we're going to draw it as a line, maybe not even a straight line, but a connection between two of our dots. So this could be an edge. Depending on limitations that we do with our edge set, we might allow things like this, which are called loops. So an edge, the pair consists of the same vertex twice. We also may allow things like this, where we have multiple edges between the same pair of vertices. We also might have a situation where order matters, and so we have ordered pairs and not just pairs. So we'll look at those different situations. We will allow the possibility of no loops, no multiple edges, and no direction. We will allow the possibility sometimes of direction, sometimes of multiple edges, sometimes loops. And it'll depend on the situation that we're dealing with. All right, so the idea is these the vertices just represent things, and the edges represent relationships between those things. So in this situation, we might have 4 cities. So the vertices represent cities, and the edges represent flights that are available between cities. So what does this mean? This means that there are flights available back and forth between cities A and B. This would mean that there's only a flight available from A to D, but there's not one available coming back. Right now, at a certain time, maybe this is, maybe in general there's a flight available, but not when you need it, right? So at this point, there's only a flight one direction. What does this mean? There are 2 flights available. And so 2 different flights, and maybe there's different, different cost or something associated with those 2 flights. What does this mean?
Engine failure.
So the flight is taking off from this city and coming back and landing in the same city.
Round trip.
But a round trip would consist of going someplace and coming back, right? What kind of thing would take off from a city without engine failure and land in the same city? Skydiving, right? Or a news helicopter. Tour guide, right? You get in the helicopter and you fly around, or a small plane and you fly around and you come back and you land where you started, right? So there's lots of situations where this would make sense. If we were talking about going on a trip somewhere, we wouldn't want any loops in our trip like that, but there could be perfectly valid explanation in some context for this. All right, so what happens is we're going to use this idea of dots representing things. Again, it may not be dots because we may have too many things to draw, so we might just represent them in some other kind of set. And then the edge set consisting of some specific set of pairs of these things. If the items in the pairs do not have to be unique, we allow for loops. If the pairs themselves do not have to be unique, that allows multiple edges. If the pairs are ordered, that gives direction, and otherwise we have the undirected, no loops, no multiple edges version, all right? So which is sometimes called a simple graph. All right, so what could this have to do with our with our queen's problem. Could we represent our queen's problem in this format? Well, let's just look at, say, a 3x3 board. We could let each vertex represent one of the squares. And what would an edge represent? An edge would represent that you can get from one place to another in one move. So what would happen? You can get from here to here or there in one move. Does that make sense? So all three of those are connected in this way. You can also do this or this. What else can you do? Same thing vertically. And then what? There's diagonals. This has already gotten really messy. And what else is missing? Yeah, these diagonals. All right, it's a really messy graph. But it turns out that sometimes it's beneficial, even if the representation is messier than this picture. What have we also added? This picture adds the fact that you can get from one place to another place. What does it show? It shows that there's no direct path from here to here. And if we just have a grid, it doesn't represent that exactly. Because the same grid is the same 3x3 chessboard. What happens if we change chess pieces? What if we change to, say, the rook? How does the rook move? The rook can only move up and down, left and right. This picture stays the same. What happens to the graph? All of that diagonal stuff goes away. Right? And so we only have a much simpler graph to look at. So this picture, doesn't include all of the information that the graph includes. Again, we don't want to look at that graph, especially on the 8x8 board. We don't want to look at that graph, but what could we do? We could represent that graph with some data structure that will hold that information and be better than just having a grid in certain situations. On the other hand, if we can find a good way to be able to tell whether two queens are attacking each other, some kind of easy computation to do, then the grid kind of idea could be really, really useful. All right, so we're going to look at a bunch of different connections, a bunch of different ideas that are related to this, and use this as our fundamental kind of structure for a lot of the rest of the term. So we're going to be able to use this to do, say, motion planning algorithms, and we're going to use it for a lot of different scenarios.
For our graph, would it be the like simple computation you were talking about? Like, if we had you erased it, but if you had like a queen in the bottom left, could you like just follow the edges out where that queen was?
So where that queen was, in the bottom left, if you follow all the edges out, you could mark all of those places that you get to as being places that you cannot place another queen. Right? So if you put a queen in one place, you can immediately mark all these other slots as you can't put a queen there, and then move to another vertex that hasn't been marked yet, and put a queen there, mark everything that you can't put a queen at. So then when you decide to back up, if you made a mistake, you back up and you take the last queen off, and all of the marks that went with it go away as well. And you can try a different unmarked spot for your next queen. So yes. Okay. So in order to use graphs to do the the kinds of things that we want to do, we need to get some understanding of how they work and what's going on and what happens. So we're going to look right now at just simple graphs. So these are graphs with no loops, no multiple edges, and no direction associated with anything. Now, the graph theory itself as a discipline started in 1736. There was a particular problem that we'll talk about a little bit later, involved walking on bridges around a city. That problem led to the creation of the techniques and the ideas. It actually was a graph that had multiple edges. So the very first graph in graph theory that was studied was a graph that had multiple edges. We'll come back to it a little bit later. Excuse me. All right, so let's say we have a graph. So when we talk about the edges are really pairs of edges again. So we sometimes will write them down as a set, like AB. Sometimes we write it as, especially if order matters, we write that with parentheses so that it's an ordered pair. We're going to be really lazy and just write it down like that. So that edge would be called AB. Even though you might be going from B to A, we don't care, right? We'll just call it edge AB. Or sometimes if we really don't care, we just call it edge 1, 2, 3, 4. Okay. Now, we look at this vertex right here, A, and we talk about an edge being adjacent to, we talk about an edge being incident with a vertex. We won't worry about that too much. A and B, we say that those two vertices are adjacent to each other because you can get from one to the other on an edge. Edges can also be adjacent. So like this edge AB and this edge BC are adjacent to each other because you can get from one edge to the other crossing at that vertex. So when we use these terms, again, we'll be a little more formal later on, but we look at vertex A, and how many edges, we'll even be completely informal, we'll say how many edges touch that vertex? There's one, right? So we talk about the degree of a vertex. So the degree of vertex A is 1.
Take a step back. So, are adjacencies only from like a distance of 1, or are A and C also adjacent?
They're not adjacent. A and C are not adjacent. It is a distance of 1. So there is an edge joining those two, or in terms of the pairs, both vertices are in a single pair. Okay. Now we will talk about the idea that you can get from A to C, but that's in terms of a distance. So a finite distance from A to C means that you can get there, but they're not adjacent. All right, so we can go all the way around. We'll write this usually something like this, the degree of A. And so the degree of A is 1. What's the degree of B? 3. And C and D both have degree 2. Okay, so let's draw a graph with 5 vertices all having degree 2. And again, when we say graph, we mean a simple graph. A way to do that is just go around the outside. Is that the only way to do that?
It's too complicated.
Are those two different? What could we do? We could kind of unfold the star and turn it into that picture, couldn't we? The order, the order might be changed of the vertices, but since they're not labeled anyway, we could unfold that star. So that's something else that we're going to look at. If you have two different drawings of a graph, do these two drawings represent different graphs, or do they represent the same graph? All right, so that's an issue that comes up as sometimes important. So this situation is, we can think about whether there's any other way to do this. But this, when they all have the same degree, is a particular, that's of interest sometimes in certain problems, and we'll come back to that again later as well. The number of vertices, we usually call the order of the graph. So the order is how many vertices you have, and size is how many edges. Unfortunately, maths folks tend to use n for the order and m for the size, and that can be really confusing because when you're saying it out loud, n and m can sometimes sound a lot alike. But when you see it written, if you see something written about graphs and you see n, it almost always means how many vertices there are, and m almost always means how many edges there are. But not always, because this idea is a pretty basic idea, and people in lots of different disciplines have stumbled onto the same idea. And so economists and chemists and social scientists and lots of people from different fields use these ideas, and they make up their own notation and their own terminology. So we'll usually probably use that notation just because I've spent a lot of years using it, so it's a hard habit to break. But sometimes I won't even use the words order and size. I'll just say how many vertices, how many edges. But if I do use order and size, this is what it means. All right, so let's look at order 6. And let's have all of the vertices again having degree 2. All right, so let's draw a graph of order 6 where all of the vertices have degree 2.
Are you able to, you have to get from one vertex and be able to get to all the others?
No, we don't have to.
So you can have, the 3 kind of separate from each other.
Yeah, we could have this instead of this. Now, what do we know about these two? Because this is all one graph, and this is all one graph. What do we know about these two?
They're not.
They're not the same. Right? Because from here you can get to everything else. From here you cannot. And so this idea is the idea, and we'll see, be more specific, be more precise. But this graph is connected, and this graph is not connected. And so that means that they are fundamentally different in some way. Whereas we don't have that same situation over here. And in fact, these two, as long as we're ignoring any kind of labels on things, are exactly the same. The relationships are the same. When we have different, you can have the same order and the same degrees, but have fundamentally different graphs. All right, so let's draw another graph. Let's say, let's draw a graph of order 6 and size 10.
Really have to say 10. Was that entirely necessary?
This is size 10 now, right? Not degree. What's the maximum degree we could have?
Oh, yeah, you did.
What's the maximum degree we could have in a graph of order 6? 5, right? Because we're talking about simple graphs. So what would happen if a vertex was adjacent to everything else? Its degree would be 5.
Our two previous. Right. Yeah.
What does size mean?
Number of edges.
Number of edges. How many edges do we have?
Why did I think it said size 6? I should probably change that.
All right, so somebody, do you have a graph?
Yes.
Which edges do you have here?
Why, if you do classic loop-de-loop.
So you came all the way around.
And then I connected F and B,
And B.
E and C, A, E, and B, D.
No.
Yeah, I mean, that works too.
You said ED. Okay, so you have two triangles here, and then these opposite. So you did something like.
I drew some lines and something.
Yeah. So something like connecting these triangles together. You kind of started here and could have done some things. You went around the outside, and then just kind of connected things that were kind of opposite in some way. All right, is that the same picture you had? Let's. What were your connections?
I connected all the way around.
All the way around.
I did B to D, D to A, A to E, and then C to F.
Is that different?
It's different in the sense that not all the vertices have the same degree.
Would they all have the same degree here?
Well, like comparing the two graphs, like F and
Okay, let's see.
IE doesn't have the same degrees in both.
Let's see what happens here. What's the degree of A over here?
4, 3. Oh, 3.
It's 3 on this side.
4,
4.
3, 4.
Okay, now what about over here?
4, 3, 3. Oh, 4, 3, 3.
So we have 2 vertices of degree 4, and everything else is degree 3 in both.
Does it matter that the ones that are 4 are different?
So what would happen? I mean, we could change the letters, right? We can move the letters around and say, well, is the picture the same? Because in the picture earlier we were saying if you didn't have the labels, are the pictures the same? Can you turn one picture into the other just by moving things around? You know, imagine these being pegs in a board with rubber bands attached between them or something, right? So can you move them around and turn one into the other? What do you think? Do you see anything different about these that would tell you for sure that you cannot turn one into the other?
Other than the line, how the lines are crossing. But,
I know a good way to make it so you can't turn one into the other. Not for these two necessarily, but one that's very obviously not the same.
So you have a different, you drew a different picture?
Yeah.
Let's see. We'll come back to this idea in just a second. So, what did you draw?
A to B, A to C, A to D, A to E, B to C, B to D, B to E, C to D,
What'd you say?
C to D, E to E, and D to E.
And what the hell? Poor F.
All along.
Okay.
Wait, is there a limit?
So what happens in that picture? For sure, it has 6 vertices, has 10 edges. And how do we know that it's different?
One's not connected.
That one vertex has degree 0, all the others have degree 4, right? This one's definitely different than these other two.
To go back to the other two.
All right, now let's come back to the other two and see, is there anything at all about them that we can tell?
Would you be able to say this is different because in the red graph it would take there's like a distance of 2 between A and D versus the blue you can get there in just 1.
Between A and D?
Yeah.
Well, what if A and D actually really mean B and E?
But you said completely different letters.
Yeah, so we said that these are the red letters and those are blue letters. And so red letters and blue letters, we can rename them. So A and whatever, A and D might not really be A and D.
Well, that's just silly.
I think
Is this kind of like they would be the same because the same regular expression would represent both of these graphs?
Regular expression to represent a graph. No. There's something fundamentally different about these two.
That one has degree 4 connected to degree 4, that one doesn't.
Yeah, if you look at the degree 4 vertex here and the other degree 4 vertex here, how far apart are they? They're adjacent to each other. Are the 2 degree 4 vertices adjacent in this graph?
Nope.
They're not. So what does that mean? That means these graphs are different. Does that make sense? So even though all the numbers are the same, the degrees are the same, it looks like, well, can you turn one into the other? What's going to happen? No matter how hard we try, we will not be able to just move these around and turn one into the other, because over here, the degree 4 vertices are a distance of 2 apart. We haven't defined distance, but they're 2 edges. You have to make 2 moves to get there, and over here, those 2 degree 4 vertices are adjacent to each other. All right, so what happens? We have 5 vertices, or excuse me, we have 3 graphs of order 6 and size 10. This one up here has 5 that are all adjacent to each other, and that one's left out. Down here, it looks like, oh, well, could we? But no, they're not the same because of that situation there. Okay, so sometimes we don't care whether 2 different pictures are the same, but often we will care. If the pictures that we've created, again, not always in picture form, but the representation that we've created, is this the same as that one? So sometimes we will use tables to represent these, because it's something that we can save and use in a program. Sometimes we will use a matrix to represent a graph, basically a binary matrix with zeros and ones, or other matrices as well that aren't binary matrices that we'll look at. And so representing these, the representation we use will depend on the problem that we're trying to solve and what we're trying to do in a particular context. All right, so let's see here. Let's draw a graph of, well, let's just draw a graph. Actually, let's have a definition first. All right, we'll say a vertex is even if its degree is an even number. And we'll say that the vertex is odd if its degree is an odd number. All right, so let's draw a graph of order 6 with all the vertices being odd vertices. It's a really easy one.
No.
There's a really easy one that satisfies that condition. What's the degree of all these vertices?
1.
They're all degree 1. No, there's lots of other choices, right? You can do lots of other things as well. So having all odd. What if we said all even?
Connect them.
Right, all even, just going around the outside would have done that, right? There's lots of choices. If we already had these in place and we wanted to make everything even, what could we do? Well, we could just build from here, right? And be able to do something to connect things and make them maybe all be even. Maybe we messed something up here. We have to delete an edge and try something else, right? What's the easiest graph of order 6 with all even vertices?
No edges.
No edges at all?
If you are,
What do we know about the number 0?
It's circle. I don't know why I said that.
0 is an even number, right? Is it divisible by 2? 0 divided by 2 is 0. That's a number. So 0 is even. So that is one with all even vertices.
Wait. So is 0 also all?
No, 0 is not
I
odd.
don't know why I just said it like that.
0 is even. Only even.
Okay.
Think of 0 mod 2. Right? What happens when you divide 0 by 2? What is the remainder? 0. What does it mean to be odd? When you divide by 2, the remainder is 1. When you divide 0 by 2, you never get 1 as a remainder. So 0 is only even.
Oh, okay.
Now what is it not? It's not positive or negative. And that is the confusing part for some people. Right? We remember the 0 is not something, but then right, it is even. All right, so let's see here. Let's draw a graph of any order that you like. And let's say the order is more than 1. All right, so draw a graph of any order that's greater than 1 with exactly one even vertex. What did you draw?
I drew 3 vertices with 1 edge.
Fourth one. What'd you say?
3 vertices with 1 edge.
All right. 3 vertices with 1 edge. What degrees do we have?
1,
1, 1, and 0. And that does it. Okay. Now what if we said draw a connected graph? So connected means that there's no separate pieces, right? Again, we're not a formal definition yet, but connected means what you kind of expect. You can get from anywhere to anywhere else with enough, following enough edges, you can get there. So let's make this a connected graph.
Yeah. Just connect the other vertices.
So what are you going to do?
Just connect the other vertices. It doesn't matter which one.
Connect that, and what do we have? 2 with degree 1, 1 with degree 2, and we're okay still. All right. So let's draw Draw a connected graph of any order with exactly one odd vertex. So what's the degree of that vertex?
Wait, that's not good.
Yeah.
What is silly? Jump to the gun should be my middle name.